So next, let's us look into a pathogen-agnostic metagenomics application. So nanopore sequencing is, I would say that it revolutionized a rapid, unbiased pathogen surveillance because traditionally, surveillance method focus on the retrospective investigations of known or suspected pathogens. However, the future lies in agnostic sequencing methods that allow for a very broad real-time pathogen monitoring, identifying what is present in a sample without prior assumptions. Like for example, the targeted surveillance will ask, is this in the sample? Where agnostic surveillance will ask, what's in the sample? So the ability, because of the inexpensive and it can be high throughput sequencing technology for nanopore, we sort of paved the way for next generations of pathogen surveillance. And through the monitorings of non-pathogens and detecting the emergent pathogen at the same times, the metagenomics surveillance enhance these um, with the capability to generate a metagenome assembled genomes, which offer a more detailed transmission analysis and better antibiotics resistant predictions. So this kind of pathogen surveillance can be very useful across hospital or across, water purification plant in farm or other high-risk location where emerging diseases are likely to originate. And again, one of the key benefits of nanopore technology in metagenomic context is that it has unrestricted read length. So it can enable a better metagenome assembled genomes and rapid access to results. This also allows a researcher to quickly gain insight into the microbial community composition and functional properties, enhancing the real-time decision making in critical scenario. So here you can see this is the bandage plots. Compare the short read and as well as the nanopore long read assemblies. So in contrast to a fragmented assembly with many shots disconnected or tangled contigs, you can see that nanopore data resulted in a very well-connected contigs, which indicates a more complete and higher quality assembly. So in this slide, you can see that nanopore technology offer rapid turnaround time for metagenomics. So in making it, one of the options that is very suitable for analyzing complex environmental or clinical samples. And these samples often have low amount of pathogens together with, high level of, materials, DNA material from hosts or like, other common microorganisms and typically requiring a specialized method for microbial enrichment. And here in this slide, you can see there are various metagenomic methods that have been developed by our customers for different scenarios. However, they all share one common trait, which is a very short turnaround time from sample to answer. Like for example, for respiratory metagenomics, um, our customer able to detect respiratory pathogens and resistant within, 7 hours. CISPA and Smart9N, they are able to detect viruses like Ebola, SARS-CoV-2, or Mpox within 6 hours. And with adaptive sampling, it can deliver results in 5 hours and can, if efficiently detect bacterial pathogen as well as antimicrobial resistance. So I think out of the the different methods, let's review one of the metagenomic protocol developed by Adela, Professor Jonathan Exworth, and colleague from Guy's and St. Thomas Hospital with the support from Oxford Nanopore. So this is the metagenomic methods developed for both DNA and RNA sequencing of pathogens. And this method can be applied to routine samples such as the nasal pharyngeal swab or the broncho alveolar ravage. And it has also successfully sequenced pathogens like the mpox virus from the skin lesion swabs. So it demonstrates its versatility across different sample types. So you can try. And this protocol cover the recommendation in the RNA and DNA extraction, followed by the cDNA synthesis using random hexamer and oligo-DT primers for the RNA in the sample. And then we just follow the standard rapid PCR barcoding protocol, which we will need to tagment your DNA, and then you PCR both your DNA and cDNA strand, and then you just attach the sequencing adapters, supply in the kit, and then prime the flow cell, load your DNA library into the flow cell. And in terms of analysis, we have WF metagenomics for identifications of the origin of single reads from both amplicons, targeted or shotgun metagenomic sequencing. So it also provides you with the intuitive reports with interactive graphics. Again, you can run it in real time to see the composition of the microbial profiles in your sample, or you can do it post run with a finer workflow that require more computing. So I think this case is a case study, the respiratory metagenomic workflow that we discussed earlier. So this nanopore-based respiratory metagenomics, um, in fact, has demonstrates a significant impact in the medical field, particularly in the ICU settings. So this is a case study that highlights the potential of respiratory metagenomic in ICU, where the workflow that we see just now is a single test that can test for bacteria, for fungi, for DNA and RNA viruses. So if I were to put it into the perspective, you can see that here the comment from the CEO of the Guy's and St. Thomas Hospital, um, that the ICU costs range from 2,500 pounds to 10,000 pounds per day, depending on the severity of the patients. Additionally, the use of the broad spectrum antibiotics has also continued to drive the antimicrobial resistance. Is a growing global threat identified by the WHO. And therefore, there is a very urgent need for a sensitive, rapid, and also less biased diagnostic tool for respiratory infections. And respiratory metagenomics so far has shown promise as a first-line diagnostic tool for lower respiratory tract infections, with the ability to detect all the pathogens and offer resistant profile to assist with the infections control and also the public health measure. And however, the questions it still remains in what is the feasibility of doing same-day testing and whether the results are frequent and informative enough for routine clinical implementation. And that's that's the reason why they have this pilot study. In this pilot study, they do this respiratory metagenomic workflow, and you can see here's the results. They have so far performed on more than 500 samples with 250 samples as part of the pilots. And the results has shows that 90% of the samples, they are able to get same-day results with the median turnaround time of 6.7 hours versus the traditional methods, culture-based method that takes 40 hours. And the sensitivity is 93%, specificity of 95%. And more importantly, you can see 45% of the cases resulted in informed antimicrobial prescription changes. and 20% escalation on the same day, 25% of the cases de-escalations mostly next day. And also, this study has also uncovered a hidden infectious burden in the ICU setting that are, often missed by, traditional testing. Like for example, one of the example is a cluster that involved three patients with 99.9999% of the genetic similarity of the Klebsiella varicola that was identified. So this incident has suggested there is a potential patient-to-patient transmission due to overlapping ward stays. So these insights has offered the potential for improved infections control, and it also can prevent further escalations if they, handle this issue more in a faster manner. So given the recognized, gap in the preparedness highlight by the COVID-19 pandemic, as well as the increasing antimicrobial resistance, which is a global issues, this study actually gives both encouragement and the urgency to introduce metagenomics for evaluation as a standard of care in acute care pathway. Especially in the ICU setting, every hour counts. If there's any improvement made to the treatment management, it can save life. So this is my last slide. Thank you for listening.